Hi, welcome to my channel, and in this video I will talk about estimation and the properties of a good estimator. So let us first go over the estimation. So in any research studies, the population of interest is very much large. Sometimes it is uncountable, infinite. So we always talk about sampling, and one of the main purpose of sampling is to know something about the population characteristics. So suppose that this is population. This population has suppose 2 million units. So our population has 2 million elements, and it is almost impossible to take information from the 2 million. So that's why we take a sample out of the population. We take a sample say of size 10,000. So our purpose here is to know something about the population based on the information collected from the sample. So based on the information from the sample, we estimate the characteristics of the population. So estimation is simply the process of making a guess about the value of the population parameter. So for example, we can make an estimate about population mean, estimate about population variance, and etc. So estimation is related to the process of making an estimate or making a guess about the population parameter. So we can give an example of the sample mean as an estimator of the population mean. So for instance, we take information from these 10,000 samples, and we find that the sample of the 10,000 units, sample units is 105, suppose 105. So on the basis of this sample statistics, we make an estimate of the population mean and say that population mean is also 105. So while making an estimate, we can follow two ways. One is the point estimation, and another is interval estimation. The distinction between point estimation and interval estimation is very simple. If we make an estimate in a single precise number, it is a point estimate. For example, if we make a point estimate to be 5.2, this is a point estimate because this is a single number, a single point of the statistics. However, we can make an estimate in an interval in a range of values. For example, we can say that the population mean lies in the range of 4.8 to 5.6, and there is a level of confidence associated with this range. Here 95% confidence. So point estimate is a single point or a single value of the statistics which is used to estimate the population parameter, whereas interval estimate is a range of values which is used to estimate the population parameter, and interval estimate is associated with a certain level of confidence. Next, let us go to the properties of the unbiased estimators, or properties of good estimator. A good estimator literally is the one that is as close as possible to the population parameter. For example, our population mean is 50. In most cases, it cannot be calculated. For now, for illustration purpose, let us consider that the true population parameter is 50. So an estimator, to be a good estimator, should be as close as possible to 50. For that, we consider certain properties of the estimator that can produce an estimate that is as close as possible to this number 50. So the first property of the good estimator, the first property of a good estimator is unbiasedness. Unbiasedness property simply tells us that if we take repeated samples from the population and find the average value of the estimator, it should equal the population parameter. So what it means that we have a population and we take different samples, sample 1, sample 2, sample 3, sample 4, sample 5. And suppose we calculate the value of an estimator x bar, and the value of x bar is 48, 49, 52, 55, 67, 42. An unbiasedness property says that if the average of this sample average, if the average of the sample average equals population parameter, or if in this case if the average of the sample means equals 50, we say that the sample mean is an unbiased estimator. So in a sense, the sample mean cannot be exactly equal to the true population parameter, but on average it can be. And if it is equal to population parameter on average, it is called an unbiased estimator. So the technical definition of an unbiased estimator is that an estimator is unbiased if its expected value, if expected value is the average value, if its expected value equals the population parameter. So we will show this concept with an example in Excel. So for instance, the sample mean is always an unbiased estimator of the population mean. So next property of good estimator is efficiency. So efficiency property is related with the degree of certainty or degree of uncertainty of the estimate. For example, to continue with the previous example of the population mean, suppose population mean is 50. Let us suppose that the distribution of the first estimator is quite flat. Means the value of the estimator ranges from 50 minus 30 to 50 plus 30. So in this case, though the estimator is unbiased, on average the estimator equals the population parameter, there is quite high degree of uncertainty, because if we take samples repeatedly, sometimes the sample mean is 20, sometimes the sample mean is 80. So we are very far from the population mean in some cases. So, however, if we consider another estimator whose sampling distribution is not that much flat, for example, like this one, so which ranges from 50 minus 5 to 50 plus 5. So in this case also the mean value is 50, so the sample is unbiased, but the variance of the samples means is smaller than the previous case. So in this case we say that the estimator with this distribution is more efficient. So efficiency is related to the variance of the sampling distribution. If the variance of the sampling distribution is lower, the estimator is more efficient. If we compare between more than one estimator, the estimator with lower variance is said to be more efficient. So in this case, suppose this is theta 1 estimator, this is the distribution of theta 2 estimator, and variance of theta 2 is less than variance of theta 1, and we say that theta 2 is more efficient estimator. Theta 2 is more efficient because with theta 2 we can produce estimates that are closer to the true population parameter, or in other words, there is less uncertainty in the estimation process. So we can clarify the concept of efficiency with the following graphs. So in all the cases the estimator is unbiased and the mean value is 80. So in all the three cases the mean value of the estimator theta cap equals the true mean value theta, but in this case the variance of the estimator is higher, so there is more variance, so this estimator is less efficient. So less efficient because of high variance. So here the variance is lower than the first case, so this is more efficient than the first case, and this is more efficient than the first and second case since the variance is very low. So we will see in a while with an Excel example what the variance of the estimator means. The next property is consistency. Consistency property is related with whether the estimator comes closer to the true population value if the sample size is increased or not. So the technical definition is the estimator is consistent if the value of the estimator comes closer to the parameter as sample size increases. So in this case, the first distribution is with a smaller sample size. As the sample size is increased, the distribution comes closer and closer to the true value 4. And if the sample size is very large, the distribution just collapses to 4. So this consistency property tells us that as we increase sample size, for example, we have a population of 2000 elements. In the beginning, we take a sample of size 20 and the distribution is quite flat. Then we increase sample size and we take a sample of 50 and the distribution comes closer to the true value and its variance falls. Again, we increase the sample size, n is 200. The distribution comes more closer to the true value 4 and the variance falls. And now we take a sample of 500 in size and the distribution comes even more closer, and suppose that we increase the sample size to 900, it just comes quite close to the population parameter 4 in this case. So the consistency property is related to whether the uncertainty in the sampling distribution or whether the uncertainty in the estimation process reduces or not with the increase in sample size. And the next property is sufficiency. So this sufficiency property is very simple. It says that an estimator is sufficient if it utilizes all the information provided by the sample. So if an estimator utilizes all the information provided by the sample, it is sufficient. For example, sample mean. So sample mean is based on all the observations, so it utilizes all the available observation. So that's why it's sufficient. Whereas sample median doesn't utilize all the information as it is based on the item on the middle of the distribution only. So in this sense, sample mean is sufficient as it is based on all observation, or it utilizes all the information, whereas sample median is not sufficient. So now let us explain this concept with an example in Excel. For the illustration purpose, our population size is very small, overly simplistic. There are only 5 elements in the population: 1, 2, 3, 4, and 5. So capital N is 5. Now we take first a sample of size 2 from the population, and as before we can draw sample in 10 different possible ways. So one sample may be 1 and 2, selecting 1 and 2 out of the 5 numbers. Another may be 2 and selecting 2 and 3 out of the 5 numbers. So if we calculate the sample mean in all these 10 possible cases, the mean of the sample mean equals 3, which is the population mean here. So the mean of the sample mean is equal to the population mean, which satisfy the criteria of unbiasedness. So here the mean of all the sample mean equals 3, which is equal to the population mean. So the sample mean is an unbiased estimator. Now let us go to the consistency property. Consistency property tells us that if we increase the sample size, the uncertainty in the estimation process reduces, or the variance of the sampling distribution reduces. So here the size of the sample is 2, and we have plotted the density function, simple density function of the sample mean. So this is the density function for n equals to 2. And now let us increase the sample size. Now in the next case we selected 3 numbers out of the 5 numbers, and there are 10 possible ways to select 3 numbers out of the 5 numbers in a different way. And again we calculate sample mean in its case. Again, we see that the mean of the sample mean is 3, which is equal to the population mean. So the sample mean is again an unbiased estimator. In fact, sample mean is always an unbiased estimator. However, with the sample size of 3, we now go to the density function of the estimator, or probably sampling distribution of the sample mean. So the sampling distribution of the sample mean is the red one now, the red one. So we see that the variance has been reduced. The variance has been reduced, and this 3 is our true value. So the sampling distribution shrinks closer to the true population value 3. Again, let us increase the sample size to 4, and we can select 4 numbers out of the 5 numbers in 5 different ways. So these are the possible samples: 1, 2, 3, 4. We can select 1, 2, 3, 5. We can select 1, 2, 4, 5, and 2 other ways. And again, we calculate the sample mean in its case, and the mean of the sample mean is again 3, so sample mean is unbiased. But we see that the sampling distribution of the sample mean has come closer with a reduction in variance. So we can see that as sample size increases from 2 to 3 to 4, the variance of the sample distribution has reduced, implying that the uncertainty underlying in the estimation process has fallen. So sample mean in this sense is a consistent estimator of the population mean. And sample mean is sufficient because it is based on all the observations that are available in the sample. So we cannot show the efficiency of sample mean here, because for demonstrating the efficiency, we need another estimator, and we compare the variance of another estimator with the variance of the sample mean. And in fact, sample mean is more efficient estimator than sample median and sample mode. Now let us go back to the confidence interval. So confidence interval is related with interval estimation. Confidence interval is simply the range in which the population parameter is expected to lie with some probability. So the interval estimation or confidence interval, it has three important stuff. The first one is the point estimator, the second one is the confidence level, and the third one is the standard error of the sample statistic. So for example, while constructing a confidence interval, we say that the population parameter lies within 5 plus minus 2 units with 95% confidence. So it says that we are 95% confident that the population mean lies within 5 plus minus 2 units. So this 5 is the point estimator. This plus minus 2 is uncertainty that is reflected by the standard error of the sample statistics, and the 95% confidence is the confidence level. For example, let us take the case of population mean, how to construct a confidence interval for the population mean. So the formula for constructing the confidence interval is x bar plus minus z alpha times sigma over under root n. So in this formula, this x bar shows the point estimation or point estimator, z alpha shows the level of confidence, and this is the standard error of x bar, which represents the uncertainty underlying the distribution of x bar. So to calculate the confidence interval, we simply need the point estimator. For example, the point estimator is 10 in our case. The standard deviation, population standard deviation is 2.5, and we are to calculate the 95% confidence interval for population mean. So we put the value of x bar to be 10 plus minus. So this z alpha in this case is 1.96. So this 1.96 has been taken from the normal distribution. So in normal distribution, minus 1.96 to plus 1.96 covers the middle 95% of the area, or middle 95% of the probability. So for 95% confidence interval, the value of z alpha is 1.96. So we use 1.96 here to reflect the level of confidence at 95%. Sigma is population standard deviation here, which is given as 2.5, and the sample size is 9 sample observations. So the sample size is 9. So if we calculate this, the confidence interval comes to be 8.37 to 10.63. So we should read this as the population mean is expected to lie in the range of 1.37 to 10.63 with 95% confidence. Or we can say that we are 95% confident that the population mean lies in the range of 8.37 to 10.63. Thank you for watching this video, and in the next video I will discuss about the hypothesis testing procedure, which is another component in statistical inference. The first one being estimation. Hypothesis testing is also an important component